right, so that's the vectors, and now let's do some math. So let's first figure out just what these two are. So let's figure out what E plus and E minus are. So I have that E plus is K times Q plus over R plus squared. So that's going to be this Q plus here, and R plus will be that distance to the plus charge. So K is 8.989 times 10 to the 9th newtons meter squared per coulomb squared. And Q is 10 times 10 to the negative third, so that's 10 E minus 3 coulombs. And the distance is 10 centimeters, so that's 0.1 meters, 0.10 meters squared. And that is 8.989 times 10 to the 9th newtons per coulomb. Kind of a lucky accident here that we sort of 10 times 10 to the negative third is equal to that. So we actually end up with the positive E just being the same as K. That doesn't normally happen. And a quick note about sig figs here. So if you're new to this class or you just need a refresher, it's kind of hard to see on the board, but you can definitely see it if you look at the PowerPoint setup for example 16.4. You can see that this 10 is written with a decimal point at the end. So this has 2 significant digits, this one has 2 significant digits, and this one has 3. So we're going to want to give our answer to match the number of significant digits and the least significant number in the problem, and that's 2. So we're going to want 2 sig figs in our answer. So at the end, we're going to want to round to 2 sig figs. So we're going to want to have at least 3 sig figs in what we're working with until the end to avoid any rounding errors. So I'm going to go ahead and just keep 4 sig figs throughout here, but when you're doing your calculations, it's a good rule of thumb to keep 1 or 2 extra significant digits throughout all of your calculations so that at the end you don't round in the wrong direction. So that's the magnitude of the positive charge. I'll go ahead and specifically say it's the absolute value because I don't want to worry about any minus signs or anything right now. We're going to get all of our direction information from our brains, not from memorizing equations. It works a lot better that way. And the magnitude of the E minus charge is going to be K Q minus over R minus squared. So that is 8.989 10 to the 9th newton meter squared per coulomb squared times again same magnitude of charge, even though it's in opposite direction, it's the same magnitude of charge. 10 to the negative third coulombs. And now the distance from the minus charge is going to be 14.1 centimeters, so that's 0.141 meters squared. And that I will plug into my calculator and say K times 10 E negative 3 divided by 0.141 squared, and I get 4.521 times 10 to the 9th newtons per coulomb. So if what I was drawing graphically before didn't make sense with the adding things algebraically, maybe this will make sense. Certainly the length of the net E vector is not this number plus this number, because those two numbers point in different directions, so they shouldn't just add, right? The length of this plus the length of this is not going to be these two numbers added together. We need to take into account the fact that one of these vectors, namely this vector here, has a component in the x and in the y direction. But that's not sort of worthless things to have done. It's still good information to have had, because now we can start thinking about things in the x and the y direction. So let's look specifically at this vector here. So I have that E minus has an x component that points to the right and a y component that points down. E minus x and E minus y. And this is a right triangle, so we can use the things that we know about right triangles to solve for it. So I'll go ahead and label this angle. And if you look at this angle, the angle that this points at is the same angle that's along this line here. And this is, I already said, a 45, 45, 90 triangle. If you couldn't figure that out from there, which means that this right here is a right angle. And if this is a right angle, there's 180 degrees in a triangle. Since these two sides are the same, these two angles also have to be the same. So this angle here is 45 degrees. And I guess that means that similarly that angle there would be 45 degrees. And that angle there is 45 degrees. All of these angles are 45 degrees. So I can use SOHCAHTOA to figure out what the length of these two are, given that I know one length and one angle. So using SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. I like to start with sine. So sine of 45 degrees is going to be the opposite side over the hypotenuse. So that's EY minus over E minus. So EY minus over E minus. So EY minus is just E minus, which we already know, that's that number, times sine of 45 degrees. And that equals, still have that number fresh in my calculator. I'll go ahead and store it. So that times sine of 45 is 3.197 times 10 to the 9th newtons per coulomb. Do the same thing for cosine now. So cosine of 45 is EX minus over E minus. So cosine is adjacent over hypotenuse. So cosine of 45 will be the adjacent side over the hypotenuse, so that's EX minus over E minus. Solve that for EX minus, and we'll get the same similar type of equation. So EX minus is going to be E minus times cosine of 45 degrees. You can plug that into your calculator, but actually sine of 45 and cosine of 45 are the same number, so I can do that in my head. This would be the same as that. 3.197 times 10 to the 9th newtons per coulomb. So now we can go back to this diagram, this way of thinking. We can actually say that E plus and E minus y both point in the y direction, so they will add like numbers, they'll add algebraically. So what I mean is that now I can look in the x direction, and there's only one vector that points in the x direction, that's E minus x, and that's that number. So EX, the net E in the x direction is going to be just EX minus, and that is 3.197 10 to the 9th newtons per coulomb. In the y direction, it's a little harder because we have the 2. So EY is going to be these two vectors added together. So that is E plus minus E minus y. I went ahead and put a minus here because I know that these point in opposite directions. So that's another example of using my brain to figure out the direction rather than memorizing it from an equation. Coulomb's law and the similar equation that goes with electric force, that's only telling us magnitude information. You need to kind of use the information that you know about the direction that these things point to figure out the direction. So I know that a minus goes here because I know that they point in opposite directions. And we're ignoring any signs of charge in any of our calculations. So we know those two numbers. There's that one minus that one. So that is going to be 4.521 10 to the 9th minus 3.197 10 to the 9th. And that is going to be whoops. Yeah. That's why it's good to redo these numbers every time. E plus here is that number. I wrote down the wrong number. So 8.989. So let's redo that. And that is 5.792. 10 to the 9th newtons per coulomb. So now we are almost, but certainly not quite done yet, which is that now we have the x and the y components of the net vector, of the net E vector that we're looking for. We know that the net vector is going to point up in one direction and to the right in the other direction. So I have that EX is here, and EY is here, and I'll go ahead and draw them adding in like a right triangle would be. And we know the lengths of both of these vectors, and what we would like to figure out is E. And of course, vectors always have magnitude and direction, so what we would like to do is figure out the length of the side of this right triangle, which we can do with Pythagorean's theorem, and also the direction that this angle points at, which we can do with SOHCAHTOA. So this is a right triangle. There's my right angle. So this side squared plus this side squared equals that side squared. So I have E squared equals EX squared plus EY squared. And I'm going to go ahead and take the square root of both sides. So that's what we'll look for. And I'm running out of board space, so I'm not going to rewrite all of that. But I believe if you plug in that squared plus that squared, you will get that the length of that vector is 6.616 10 to the 9th newtons per coulomb. Now we are finally done with something, so we can go ahead and round that to the 2 sig figs that we were looking for. So that is 6.6 times 10 to the 9th newtons per coulomb. All right, so now we have the magnitude of the final vector, and what we need to figure out is the angle of the final vector. We have the length of all 3 sides of these vectors, so we could use sine, cosine, or tangent to figure it out. In the book, usually you see them using tangent here, so tangent is opposite over adjacent. So I'm going to do that here, but if you used sine or cosine, that would work too. So I would have that tangent of this angle is opposite over adjacent. So tangent of theta, and I'll just, is EY over EX. And we're solving for theta here, and so the way that you do this is with the inverse tangent function in your calculator. So if you push second, if you look where tangent is, usually underneath the tangent button on my kind of graphing calculator, I push second, and then there's a tangent to the -1. That's the button that you want to use. So you can solve for theta here. You can't just divide by tangent. You have to solve for theta by taking an inverse tangent. So theta is inverse tangent of EY over EX. And that is 61.1 degrees, but I'll just round that to 61 since I know I just need 2 sig figs. I want to talk a little bit about angles before I end here. So let me turn this so you can see a little bit on the edge. That angle 61 degrees could be a misleading angle where you might not necessarily know what it means. And so what I mean by that is that I drew it like this, and I found this angle to be 61 degrees. But I could have just as easily drawn y and then x, and then I would have gotten, if that was 61 degrees, I guess I would have gotten 29 degrees as my angle. You know, both angles would be correct, but they're not specific. So what you could do is either a couple of things. One is that you could write the standard way that one writes angles, which is that you think about this being the x and the y directions. We measure this angle as 0 degrees, something that points out and to the right is 0 degrees. You go counterclockwise kind of a way. That angle there is 90 degrees. Keep going all the way, that angle is 180 degrees. 270 degrees, and then all the way back to 360 degrees. So if you only give an angle, you need to give it with reference to that is 0, and positive counts counterclockwise, negative would count clockwise. So writing this as 6.6 10 to the 9th at 61 degrees would actually be fine. But if you wanted instead to write it at 29 degrees, what you could write is 29 degrees to the right of the positive y-axis. Either would be fine. So if you're not going to reference your angles in this way where you count up from 0 going in this direction, then just be specific about sort of what quadrant you're talking about. So to the right or the left of the y-axis, or to the up or down of the x-axis is how you can be specific with that angle. All right, so we're done here, and I will see you in class.